Hello, everyone. This is Professor Ma, and now these sections on the computations of derivatives. In particular, we're going to talk about the computations for polynomials and rational functions. Okay, algebraic functions. Uh, we really cannot go through every formula using the definition of difference quotients to calculate the limit to derive the derivatives. Okay, so the strategy of finding derivative is we know what most formula are made from, the three families of formulas, and they are made from operations as subtract, multiply, divide in composition. So the strategy of calculating derivatives is you design any formulas that's made of multiple parts of from different formulas. How do we take it apart when we take derivatives? So what, in other words, what is the derivatives? How does the operation behave on the derivatives? So, and those we can answer. Okay. And the process of taking derivatives and the limit of difference quotient, we call that process differentiation. Okay, so and the basically differentiation is a limit province, and so when we have add and subtract, if the limit of individual component exists, then I can take the limit of the sum. It's the sum of the limits. So we got some two basic okay derivatives rules. Okay, here's to simplify the writing. We use the prime in whatever things that's being primed. That we means usually these things something in formula x. We mean the derivative of that things with respect to dx. Okay, so we use a prime procedure. It's a little easier to write than that one. Okay, we'll come back to that when we need it. So if I take the derivative of the sum, then it's going to be the sum of the derivative. But basically just rearranging these symbols, and then you can clearly see this it's derivative of the sum. It's adding individual derivative. Same thing with the difference. You just replace by a minus sign. Okay. And that's reasonable because if I have two functions and the derivatives are the slopes, so if the slope at a point A is 1 one is 2/3. Now if I were to add the two formulas together, I get a steeper formulas, and the slope at that point of the sum will be the sum of the two inclinations, 1/2, that'll be 1. So that's what basically in geometry what this rule says. Likewise, I can multiply a formula by a constant, then the limit, I can take the constant out. And so I can take the derivative of the constant multiple is the constant times the derivatives. Okay, so slope of 2x minus 1 is 2. So if I were to multiply by constant 3, then it will be 6. Okay, multiplied by c. And here is where things becomes the which usually when we say the take derivative, these are the rules we have to watch. One is regarding to product. The derivative of product is not taking products of the derivatives. It's just not. And the same thing with quotients. Okay. And here is the respective product rules and quotient rule for taking the derivative. Okay. And this one is the product rule. Okay. And this one is easy to remember it because it's symmetric. You take the derivative, one thing is times original, the other one then switch the row, then you add. But the derivative of the quotients, it's not symmetric. Okay. And if we call this high and this low, then there's a phrase for this is a high d low high derivative of low high times derivative of low minus low d high, low times derivative of high. And this is just a trick, and the whole thing over low square. And this is just a trick of remembering this formula. And you can find the justification for these formulas on the following links. So we won't go through it. And basically, this is what the geometry of the product rule says. Okay, suppose I have it's related to a rate of growth. Suppose I grow the side of a rectangle f by a little bit more delta f, and grow the length of the rectangle a little more delta g. How much does the rectangle itself grow? That's the shaded part in gray in that little piece on the corner. And that's approximately the growth, therefore, is the shade area. And it consists of that plus the two strips plus a little corner. And the derivative basically, well, the rate of growth is roughly by dropping that little piece in the corner, therefore it's equal to f times delta g plus the other one switched around. So this is basically what the product rule is telling you about rate of growth in terms of derivatives. Okay, so now let's come to the derivative of power formula. Or start with the power formula. Derivative of constant functions is 0. Derivative of x, which is the slope, which is everywhere, is 1. So derivative of the constant function is 1. Okay, and now remember the product rule. The product rule is f prime g plus g prime f. So x squared is x times x. So if I do as a product, I invoke the product rule, then I get the derivative of x squared is 2x. And if I multiply x squared by another x, okay. Oh, so here's the example how we take the derivative of minus 2 times x squared. We take the constant outside first, then take the derivative of x squared, which is 2x. So okay, the derivative of minus 2x is that. Okay, derivative of that is that. So now we can take derivative of simple polynomial like this, or any square formula. Okay, I can take the derivative of that. Let's keep pushing this. How about derivative of x cubed? Okay. So, well, we'll take x squared times x, and then we can push, say, take the product rule again, and then we find out the derivative of x cubed is 3x squared. Okay, go to the product rule. And if we sit back and do this, keep going, x to the fourth, x to the fifth, and it start like the pattern start coming out, and here is the pattern. Okay, if you do x fourth, it's going to get 4x third powers, and it keeps going, then we get that, and then look at it for a while, then we realize then here is the derivative of x to the nth power. This is n times x subtract. Take the power 1 away. Okay, so this is a first important derivative formula is for x to the nth power. Okay, over here n is integer, but actually we can extend this with, okay, we're gonna prove, okay, to any real number power. Okay, so anyway, so this is back to the nth power. So this is the formula in the dx notations, dy dx. I mean the delta y delta x notation. Okay, dy dx. But what is y? Y is x to the nth power. So that's where the notation came from. So derivative of that. So I'll let you kind of go through these, and these go through each steps, pulling out constants, using the power rule up here, and so I can apply to x sevenths, x thirds, x squared, okay, etc., and use a power rule. I obtain the individual derivatives, multiplied by the constant we pulled out. Voila, there's a derivative. And these work for any polynomial. Okay. The product rule, the two ways we can do this. We can expand this and multiply it out and take the derivatives. Okay, and it will be minus 6x cubed plus minus 2x squared, etc., 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 and take the derivative of that. I'm going to take the derivative of this. Or we can take it to product. Okay, so here is the product relations. Okay, using d dx. Okay, f times g prime. Okay, derivative of the other factors. Then g times f prime. It doesn't matter which one you do first because it's a plus. Okay, and clean it up. Check that if you were to multiply these out first, expand, and then you take the derivative, you wind out exactly with the same answers. Okay. Oh, that's what I'm doing. This, yeah. Maybe check these two answers. Let's see. Yeah, I did it for you. Okie dokie. Now what? Oh, how about if I make a quotient of them? That's where the quotient rule comes in. High D low minus low D high divided by low square. Okay. Low square, high D low minus low D high. Okay. Yeah. Then just do the algebra, clean it up, and this will be the derivative. So we can take the derivative of all rational functions. Now we're going to make a leap, saying that actually this formula works for any power p. It doesn't have to be integers. It could be 1/2 for square root of x, or it could be x to the pi power, any real number power. Okay, so that enables us to take the derivative of all this stuff, formula with radicals. How? We change them into fractional powers first. Okay. Fifth root is 1/5 power. So and I distribute the 1/5 to the constant. Why? Because I'm going to take that out. It's a multiple. So I don't have to deal with that out. Okay? That the only derivative I have to deal with is actually the 2/5. And that's where the power comes down. 2/5 comes to the front as a multiple. And then take the power is take away one extra. Okay? It's minus 3/5. Okay? And that's it. That's it. Yeah. For derivative of general radical formula. Okay. From here, with this and with the product of the quotient, I can take the derivative of all the algebraic formulas. Okay, that's it. And until next time, bye bye.